Resonance and formal charge. Resonance is two or more Lewis structures in which the connection and placement of the atoms is the same, but the arrangement of the electrons is different, yet still obeying the octet rules. Let's contrast that with an isomer in which there is a different arrangement of atoms. Ozone and bond length. Ozone is O3, and we'd like to draw a Lewis structure. 6 valence electrons, 3 atoms, total of 18. And we end up with O attached to O attached to another O. And if we start to place our bonds around 1, 2, 3, 4, 5, 6, 7, 8, and I end up with a 9th. And you can see that the oxygen on the end does not have an octet. You have ended up with oxygen in the middle without an octet. Either way, we need to erase an electron unshared pair and place that electron as a double bond, resulting in ozone. But certainly we could resketch that exact same structure, but this time put the double bond on the left-hand side and end up with an equivalent structure of ozone. This is called a resonance structure. Now, you may be asked explicitly on your AP exam to draw 2 resonance structures. If that's the case, you would indeed do that, draw 2 resonance structures. Or you may be asked implicitly, and that question will come to you in the form of, explain why the bond length studies have demonstrated that the ozone molecule does not have a short and a long, which you would expect this to be a shorter bond and this to be a longer bond. Rather, the bond lengths are equal and intermediate, and somewhere intermediate in between a double and a single. So the way we want to express resonance structures, neither of which is actually correct. You don't necessarily have to show them bent, though this is a bent molecule. But what's important is we'll use this double arrow. This does not mean equilibrium. From the context of the question, you would know this is not an equilibrium arrow, but it's an arrow to represent resonance structures, in the sense that neither one is actually correct, but they both contribute, meaning the molecule doesn't actually flip between the two structures, but is an average of the two. Thus, we never get to see a shorter bond and a longer bond, but instead a blend of the 2 bonds. In a similar way, you can imagine the color blue and red blends to make purple. Or you could imagine a horse and a donkey. When they blend, you come up with a mule. It's not as if the mule is one day a horse and one day a donkey, but it's always a mule. Perhaps more relevant for some of you, dogs. If you have a shepherd and a lab and you end up with a mixed dog, it's not as if sometimes your dog is a shepherd and other times it's a lab. It's a mixture. In some textbooks, you may see this structure and this structure which we've already drawn, and don't worry about the dots. You may use dots and lines anytime you want. AP will accept either. Even if they say electron dot structure, you certainly can still draw lines. Some books, instead of putting the double arrow in between to represent resonance structures, may blend and use this notation. Do not draw this on your AP exam. Dinitrogen monoxide, N2O. 5 times 2 plus 6, that'll be 16 electrons. You're asked to put a nitrogen in the middle, an oxygen on one side, and a nitrogen on the other side. 2, 3, 4, 5, 6, 7, 8. And so then you'll notice that, of course, both the oxygen on the right and the nitrogen in the middle do not have an octet. That means we're going to need to draw some multiple bonds. So we'll erase and take an electron pair off the nitrogen that has plenty and share it with a double bond. And now notice that both nitrogens have enough electrons, but the oxygen on the right-hand side does not. So we'll erase another electron pair and put a double bond. Now go ahead and draw as many resonance structures as you can. There's three possibilities that you can see represented here: a triple bond between the two nitrogens, a triple bond between the nitrogen and oxygen, and then the two double bonds that we drew on the earlier page. Is one resonance structure better than the other? Yes. Does one resonance structure contribute to the overall formula? Yes. And so introducing formal charge. This is not a real charge, but rather a bookkeeping system. We'll use it to assess resonance structures. How do we calculate formal charge? We will take the number of valence electrons an atom has in the periodic table, subtract the number of non-bonding electrons, and subtract the number of bonds surrounding that particular atom. Now let's be clear that we never will apply formal charge unless AP asks you explicitly. So let's practice with this middle structure. If we consider the nitrogen on the left, nitrogen has 5 valence electrons. Subtract 6 for the non-bonding electrons surround it. Subtract 1 more because of the bond that is attached, and we'll end up with a formal charge of -2. 5 minus 6 minus 1, -2. The nitrogen in the middle has 4 bonds around it. 5 minus 4 will result in a +1. And the oxygen on the end, oxygen of course has 6 valence electrons, and so 6 minus 2 and minus the 3 bonds, so 6 minus 5, also a +1, resulting in an overall formal charge of 0. For neutral molecules, formal charge needs to add up to 0 because the molecule does not have a charge. If you were applying formal charges to an ion, the formal charges should add up to the ion. So you can see, if we preview, if we look at the formal charge, here's the one with the -2 and the +1. And so we end up with a -1 and a +1 in the left hand and the right hand structures. Well, all formal charge being 0, formal charge values of 0 would be best, but we don't have that. If that's not an option, then the least amount of formal charge would be best. That makes this structure not as contributing to the overall. And so how do we decide between this one and this one? If equal amounts of formal charge, the negative formal charge should reside on the more electronegative atom. Since electronegativity increases up and to the right, oxygen is a more electronegative atom, making this structure the contributing or the major contributing structure to N2O. And in fact, bond length studies have shown a triple bond and a single bond length in this molecule. Now, why not the isomers shown here on the right? Why not those? Well, you can see that their formal charge is even worse, with a +2 and a -2 and a +2. And that's why N2O is not a structure with oxygen in the middle, but instead this structure. Now, another way AP could ask this is, let's consider carboxylic acids. In particular, let's think about acetic acid, who's may be familiar with you, HC2H3O2. And AP generally wouldn't throw you and say, just draw a Lewis structure for that, but might give you some help. And so the question, as shown here, arrange the remaining atoms as appropriate around this carbon, filling in all of the electron pairs and non-bonded pairs. Sometimes AP may help you with the structure by showing what's known as an expanded format. We should have ended up with this structure, and so we have followed, per usual, we've followed our honk 1, 2, 3, 4, where the oxygens have 2 unshared pairs each, as you can see, and carbon has 4 bonds each, the hydrogen has 1 bond each, and oxygen each exhibiting 2 bonds. Each oxygen exhibiting 2 bonds around it. So AP might not ask you to explicitly draw resonance structures, but instead they might say bond length studies indicate that the lengths of the carbon-oxygen bonds in acetic acid are different, yet in the conjugate base, the oxygen bonds are the same length. Well, first, to answer that question, we need to know which hydrogen actually drops off to produce the conjugate base. And so hopefully from your acid studies you're aware that this will be the hydrogen that ionizes. So after the hydrogen ionizes and we end up with the conjugate base with a negative charge, we could of course put that in square brackets. What we notice is the double bond in the oxygen could resonate and end up here instead of here. And that resonance actually helps to stabilize the conjugate base. By virtue of allowing the electrons to spread out, we call this delocalization of electrons. Now, why don't we see resonance in the acid molecule? Because if you move that double bond from here to here, you'll end up with this structure shown, and you can see that that structure will have formal charge and is not an equivalent Lewis structure.